Hello everyone, myself N.Uday Ranjan Goud, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology. So in the previous sessions, we have seen the experimental determination of critical load, and even we have seen how to find out the critical load for the elastic zone, and we have seen how to find out critical load for the inelastic zone. And also we have seen in the previous session that instability of stiffened panels. So for different conditions, usually they rely on the semi-empirical methods. We have seen the various critical stresses formula for different conditions. Now in this module, we are going to discuss on failure stresses in plates and stiffened panels. So when I say failure stresses, so usually we know that failure condition is the instability that occurs in the plates or stiffened panels. So they go beyond the elastic range and they go into the plastic range, and whenever the failure occurs, so finally, so these are nothing but up to the elastic zone. Usually the stresses you can consider, they are uniform stresses you can consider. That means homogeneous stresses, and then you can consider like it follows a condition like when you try to take a Young's modulus and then followed by the strain. Okay, so the failure stresses. So we have discussed in the previous one, that is a stress we have considered the critical stress for the plates, that is sigma critical equals to k pi square e divided by 12 into 1 minus nu square into t by b whole square. So that is taken. And when you try to discuss about these failure stresses, so usually these failure stresses are again given by the empirical results from the various scientists. If you look at into this module, and the learning outcomes in this module are the students are able to analyze failure stresses in plates and stiffened panels, and the students are able to determine the strength of the panel to which the stiffeners are attached. So if you try to define failure stresses, what happens is plates they retain some of their capacity to carry load even through a portion of the plate has buckled. So the ultimate load is not reached until the stress in the majority of the plate exceeds the elastic limit. So the theoretical calculation of ultimate stress for the prediction of the failure stresses is difficult because it follows the non-linearity results from both large deflection and also in the inelastic stress strain relationships. So when you look at the stress strain curve and for any mild steel, and you're going to get a curve like this, okay, and therefore up to here you can consider it as elastic zone, and after that you can consider it as plastic zone. And so this is in the inelastic range, and theoretical calculations for this inelastic range it becomes little difficult, a little tough. So therefore we usually rely on the semi-empirical results or empirical relationships. So now if you look at that results, and there are various scientists that have proposed many different solutions for the failure of the plates, in which they found out failure stresses according to the type of edges they considered. And the first one we see here is Gerard, and Gerard proposes a semi-empirical solution for the flat plates which are supported on all the four edges. And after elastic buckling occurs, theory and experiment include that the average compressive stress, that is sigma A in the plate, and the unloaded edge stress, that is sigma E, so both are related by the following expression, and that is given by sigma A dash, sigma A bar divided by sigma critical, that is equals to alpha 1 into sigma E by sigma critical all to the power of n, where we know that the critical stress, that is equals to k pi square E divided by 12 into 1 minus nu square into t by b whole square. Now, so where here we considered alpha 1, so alpha 1 is nothing but any unknown coefficient, and again sigma A dash is nothing but the average compressive stress, and sigma E is nothing but the unloaded edge stress we considered, and sigma critical stress is the general formula. Okay, so Gerard he has given the critical stress formulas like this. Okay, so sigma A bar for, and again he considered the different conditions here, that is the flat plate supported on all the four edges. Okay. And if you try to look at the other one, that is the theoretical work by Stovall and Mayers, they show that the failure occurs when the stress along the under edge is approximately equal to the compressive yield strength, that is sigma Cy of the material. So earlier we have seen the Gerard, and he proposed a semi-empirical solution by assuming that the flat plate which is supported on all four edges, and he considered the average compressive stress sigma A dash, and then he considered the unloaded edge stress, that is sigma E, and he gave the relationship between these two by making use of the critical stress. Now in this, Stovall and Mayers, what they did is, and they assumed that the failure will occur when the stress along the unloaded edge is approximately equal to the compressive stress of the material, which is sigma Cy. So what they have done is nothing but they have given again relationship between compressive yield strength, that is sigma Cy, and by taking in along with the sigma critical, and they have given as the formula as sigma F dash divided by sigma Cy, that is equals to alpha 1 into sigma critical divided by sigma Cy whole to the power of 1 minus n. So this is the relationship they have given for the prediction of the failure stresses in the plates. Now after this, what happened here? Again Gerard, he extended the prediction of local failure stresses for the plate elements of the thin walled column, and he extended this the work that is given by Stovall and Mayers, and then he has given another relationship, and that is given by sigma F dash divided by sigma F Cy, that is equals to beta G into GT square by A into E by Cy whole to the power of 1 by 2 whole to the power of M. So here he has extended the concept of Stovall and Mayers that is given, and he has given another formula with his experiments, and in which again A is the cross-sectional area, and beta G and M are the empirical constants, and G is the number of cuts required to reduce the cross-section to a series of flange section plus the number of flanges that would exist after the cuts are made. So the prediction of in this whole formula, the prediction of the value of G is very, very important, because G is nothing but it is the summation of number of cuts that are required to reduce the cross section to a series of flange section plus the number of flanges that would exist after the cuts are made. So number of flanges. So G is the summation of these two, the number of cuts that are required to reduce the cross section to a series of flange section plus the number of flanges that are existing after the cuts are made. So thus for a section of the panel consisting of a stiffener and with a width of skin which is equal to stiffener spacing is slightly modified by Gerard, and again he has given another formula. So he has given the formula as sigma F dash divided by sigma Cy, that is equal to beta G into G into TSK into TST by A into E by sigma Cy bar whole to the power of 1 by 2 and M. So if you look at the two formulas which are given by Gerard, so this is one formula in which he is made use of the work of Stovall and Mayers, and he has given the expression, and after this he considered another example, another assumption, like he considered the width of the skin which is equal to the stiffener spacing, and he modified this equation and given us another equation. So again this is a similar equation, but except that here you can see here in this place, that is GT square by A, and he has given us the T square instead of the T square, and he used the thickness of the skin TSK, and he used the thickness of the skin thickness of the stringer, that is TSK and TST, whereas in the previous formula which is proposed by the Gerard, that is simply you have T square, that is thickness, and here he has given very specifically, that is the T square has been bifurcated into TSK and TST. So this is another formula that he has given for the prediction of the failure stress of the plate. Now if you look at this one, so these are the various cross sections you can see in which the values of G are predicted, and the first one you can see here, it is the angle section, and it is a basic section, and which is taken as G is taken as 2, the number of cuts that are required, because there are only 2, this is 1 and this is another one. So there are only 2 cuts that are required, and there are no more flanges that are existing after the cuts are made. So therefore it's simply G equals to T. Now if you take the second example, that is a tube, and for making this tube, again here you can see there are 4 cuts that need to be made, and the first cut, second, third and fourth. So the 4 cuts, and once you made these 4 cuts, and you can see there are 8 flanges that are occurring here. So the 8 flanges are 1, 2, 3, 4, 5, 6, 7, 8. So 8 flanges. So 4 cuts are required, and then after cuts are made, there are 8 flanges. So totally if you try to add, it becomes 12. So the G value is 12, which is to be substituted in the formula for here to get the failure stress prediction. Now simply again, if you look at it in the next one, that is T section, again here you require one section here, and you require one section here too, and after making cut here you are getting 2 flanges here. Okay, so finally that is you are going to get one section here. So this, for this kind of thing, you can consider it as 3, or otherwise you can consider like this also. This is one cut which you need to make, this is another cut which you need to make, and this is another cut you need to make. So finally there are 3 cuts which are required for this T section, and you can take it as G value as 3. And if you look out for the cruciform section, and this is one cut you require, this is another cut you require, this is another cut required, and this is another cut required. So totally there are 4 cuts that are required, and it becomes like a 4 flanges. So the total value of G can be taken as G equals to 4 for this cruciform section. Now if we'll try to look for the I section, and I section, we know that it composed of 2 flanges and 1 web, and so one section, that is if you try to make as one cut section here, and this you can take it as 1 flange, second flange, third one, fourth one, fifth one, sixth one. So 1 cut is required for this I section, and 1 cut plus 6 flanges, total the G value will become 7. Okay, so G is the empirical constant. And if you look at it for the Z section also, so 1 cut if you make here, again 1 cut plus it becomes 4 flanges, 1, 2, 3, 4. So 4 flanges, to total together the G value will be 5. So this is a way we try to find out the empirical constant G for various cross section. And once you find the empirical constant G, and you can substitute in the formula that is given by the Gerard, either into this formula or into this formula, through which you can able to find out the failure stress in a stiffened panel. So if you try to take an example for a problem, a thin square plate of side A and thickness T is simply supported along each edge and has a slight initial curvature giving an initial deflected shape, that is W naught equals to delta sine pi x by A into sine pi y by A. If the plate is subjected to a uniform compressive stress sigma in the direction, in the x direction, find an expression for the elastic deflection W normal to the plate, and show also the deflection at the midpoint of the plate can be presented in the form of a Southwell plot, and illustrate your answer with a suitable sketch. Okay, so this complete one. So first what we need to find out is nothing but the elastic deflection. Find expression for the elastic deflection of the plate. Okay, that's very important. First you have to calculate the deflection of the plate, and later you have to discuss whatever you are getting with the means of Southwell plot. So that's the question. And he also mentioned that in initially it is initial deflected position is given, and we know that for the solution of this problem, W naught is the initial deflection of the plate, and after applying a load, and here he has given sigma, that is compressive stress that is given. So applying it's going to get further curvature, W1 change in curvature. So the total deflection would be summation of both, that is W1 naught plus W1. So we have seen in the derivation that W, when you take initial you can assume as AMN as unknown coefficient, and in the W1 you will write BMN as unknown coefficient, and then you write BMN in terms of AMN, that even we have seen the formula in the previous sessions also. So by making use of the concept of this thin plate with initial curvature, you can take the formulae from this and then you can solve this problem. So W, you can consider it as W naught, and which is taken as A into sine pi x by A sine pi y by A, and then you can consider the change in the deflected shape after applying the load, and you can get the unknown coefficient as Bmn, and we have seen the formula as Bmn in terms of Amn, that is Bmn equals to Amn into Nx divided by pi square d by A square into m plus n square A square by mb square whole square minus Nx, and in which you can assume m equals to n equals to 1 for square plate, and he has given, and A equals to B also you can assume because it is a square plate, and Nx instead of Nx you can consider it as sigma, and that is taken, that is given in the question. So when you do this, and you're going to get the W, that is you're going to get the unknown coefficient as delta into sigma t divided by 4 pi square d by A square minus sigma t. When you try to write in terms of Southwell plot, this you're going to get into sine pi x by A into sine pi y by B, and the deflection WC at the center of the plate. At the center of the plate, we know the boundary condition, that is x can be substituted as A by 2 and y equals to A by 2 you can substitute because it is a square plate. And when you try to substitute these conditions into this one, you are going to get the deflection at the center, that is WC equals to delta sigma t divided by 4 pi square d by A square minus sigma t, because A by 2 or B by 2 when you substitute into this, you are going to get sine pi by 2 sine pi by 2 which is equal to 1. So this is a deflection at the center. Also here the sigma t tends to this value 4 pi square d by A square when W tends to infinity, that is deflection tends to infinity, and sigma t tends to critical value, that is Nx critical, so that the buckling load of the plate, it may be written as WC equals to delta into sigma t divided by Nx critical minus sigma t. Further, it can be written as the deflection into sigma t divided by Nx critical divided by 1 minus sigma t divided by Nx critical, and from which you can write a form of the Southwell plot, that is WC, that is equal to Nx critical into WC by delta t sigma t minus delta. So therefore, a graph of WC versus WC by sigma t will be plotted, and usually it is a straight line of slope where Nx critical and it will have intercept of delta. So this is the Southwell plot. Okay, so this is a Southwell plot what we have. Okay, so from this Southwell plot you can able to clearly calculate the deflection form of the plate from the experimental data. Okay, so that's it for the today's session, and let's try to meet in the next section with another topic. Thank you. So thank you everyone. This is the session what we had today. In the next section we discuss for the another topic, and the topic name is what we have, tension field beams.